Hey everybody, it's Mr. Molcash again, and we're back with another wonderful video from Calculus BC. This one's in 7.9, has to do with the logistic model, um, and I'll explain what the logistic model is. First of all, we have two differential equations. The one on the left here should be familiar to you. So let's talk about what that is. That's the rate of change of y, or the slope of y over time. And by the way, both of these we're assuming that y is a function of t, right? Or sometimes we call it y of t. T is implied in here as the input variable, okay? Now you don't see any t's in these equations, and that's because the rate of change doesn't depend on t. The rate of change depends on the amount present at time t. So the more stuff you have, the faster it grows. That's kind of how this works out. And the solution to this one is easy to do with separation of variables, right? You can do dy over y equals k dt and solve this, and you get y equals that should be a c, a constant of integration, my fault, times e to the kt. And you might remember in either Math 3 or if you're watching this from another class, Algebra 2, this is the model for continuous compounding, where the k is the interest rate and the constant of integration is the amount present, the initial amount. Right? At time 0, this drops out and you get the initial amount. And then r is the interest rate for continuous compounding. And so all that is supposed to be old news, right? You're supposed to have learned about this in Calculus AB, or at least how to do the separation of variables technique. And what that looks like under certain conditions, if it's exponential growth for the right amount of exponential, the rate of proportion here, the curve kind of looks like that, right? Exponential growth. Logistic model is this one over here. And what's happening with the logistic model is you've got this rate of change that's dependent on the amount present times a constant, right? So the more stuff there is, times this a minus y. And here, a, you need to know this, or write this down. A is called the carrying capacity. Okay, so y cannot exceed a. The maximum amount available for y is a. It's called the carrying capacity. So what that means is that this can only grow so much for y up to an amount. Okay, and what that turns, I'm not going to show you what the solution is to this because we don't have to solve this for y. It's a neat little exercise. You can solve this using partial fractions if you do this. It's just separable, but a little complicated because you have to use partial fractions to do that. And we don't need the solution, but we do need to know what the graph of the solution looks like. And the graph of the solution, under certain conditions, looks like this, right? So there's an amount y equals a that this kind of levels out at, and then there's an initial y value, and in this most cases the initial value is 0. So if you don't have any stuff, you're not growing, but if you reach the carrying capacity, you've also stopped growing. Okay, it's really important to know also that there's an inflection point. Whoops, I'm going to have to get away from this screen here, but there's an inflection point where we don't know what time value this is, but this line that goes through the inflection point, and I apologize for the colors, is half the carrying capacity. All right, half the carrying capacity. So let's get away from this screen here since the thing's color changing really crazy. So there's an analogy that I kind of have for logistic growth that I think is a good one. And maybe you've heard people say this in your lifetime, but I can only handle so much on my plate. And so think about a dinner plate and the amount of food may be on your plate is A, is the carrying capacity. You can only eat what's on your plate. Once you've reached the limit, the amount of food that's on there, can't eat anymore. No more stomach growth, right? Your stomach can only handle so much. You can only put so much food in your body at one time, that kind of thing, right? And so if we think about drawing maybe a horizontal line here, we've divided the plate into two pieces. Maybe the y is the amount that you've eaten at time t, and then this is the amount left over, right? A minus y. And of course, if you add these two quantities together, you get the carrying capacity, which is all the food on the plate, right? So as you eat food, right, this line maybe moves to the right. So you have more of y and less of what's left over, right? So what happens is when you've eaten half of your food, then this turns out to be the half, right? A over 2. You've eaten half the food on the plate and there's half left over. At this point, there's maximum growth happening. The rate of change is at its maximum, right? Maximum slope here. And after you've eaten half of your food, then you start slowing down. You're still eating food, right? There's still food going into your body, but you're starting to slow down until you've reached the carrying capacity. Okay, so let me back up here and see what happens as you start eating all the food, right? So when we're near about finished with what's on the plate, you know, you're starting to slow things down a little bit because your stomach is starting to feel full and there's only so much room left in your stomach and there's only, again, I can only handle so much on my plate. That's the kind of way of thinking about logistic growth, okay? I'm going to look at a couple of delta math problems before we close this video up. And I really don't like the default red color here, so I'm going to switch to that dark purple that I like. Delta math has some different problem types. This one has to do with the inflection point. This is a really easy question. You just look at your differential equation, and this is your carrying capacity. This is your A, right? It doesn't matter what was there in the beginning or how fast it's increasing or any of that. It's just asking when is the population growing the fastest, and that would be at 960 divided by 2, which is 480. And that's all there is to that. You just take half of your carrying capacity, and that's where your inflection point is. And bam, that's all there is. That's pretty simple if you know what you're doing, okay? If they're asking you about the carrying capacity, sometimes they have an alternate version of this where they have 1 minus P over 974. The carrying capacity happens where this part here is equal to 0. So remember, if P is equal to 0, if there's no population, then we have no growth, right? But at the carrying capacity, we also have no growth, right? So in the beginning of P, we have a slope of 0, but at the carrying capacity, where P is equal to A, we also have a slope of 0, right? So we can take advantage of that, and we know that P is equal to 0 is going to give us no growth. But the limiting value is where this other part, the leftover in the plate, is equal to 0, right? So this would be the leftover stuff. And if you set that equal to 0, then of course P has to be 974 because 1 minus 1 is 0, right? So that's going to be your limiting value, or otherwise known as your carrying capacity. So just make sure that you set both parts of this equal to 0, and the one that gives you a positive value of population or Y value is going to be your carrying capacity. Okay? All right. Also, they're going to ask you about the rate of change at these limiting values, right? So here there's a differential equation, and they're asking about the limit of the slope of P. This is the rate of change of P. So They're not asking about P itself, they're asking about how fast it's changing. And of course, we just said that in the logistic model that as time goes by, as t approaches infinity, this curve starts to level out and become horizontal, right? So if it starts to become horizontal, then the slope of that curve as t approaches infinity would be 0, okay, at the end, right, since there's a horizontal asymptote at the end, okay? They will ask you about concavity in the value of the second derivative, but remember that concavity changes at the inflection point, right? So we have this curve that looks like this. Our carrying capacity would be 970, right? That would be P equals 970. And down here there's no population. And then the inflection point happens at half of that. So what's half of 970? 485, right? Okay, so before the population reaches 485 algae in the tank, we're concave up. After that, it's concave down, right? So in this little box here, I'm just going to say, okay, what values of P is the graph concave down? It's for any population greater than 485, right? Uh-oh, what'd I do wrong? Oh, my fault. I realize now what I did. There is a carrying capacity, right? You can't have population indefinitely increasing. So my fault. It's between 485 and 970. So totally made a mistake there, but hopefully you understand why that's the case. In fact, let me do another problem here. And I'll explain why I messed that up. So here's our carrying capacity, right? Our carrying capacity is 574. Half of 574, what's that? 250, 27, 277? I think that's right. Nope, I messed up. We need 20 more, so that should be 287. 8 times 2 plus 1, yeah, it should be 287, okay. And our carrying capacity is at 574, so between these two places, the graph is concave down, right? It doesn't have any concavity after the population reaches its carrying capacity, so that's where I messed up before. So this, if I'm kind of rushing through this a little bit to try to save time in this video, but hopefully you see what I did there, right? Take half of your carrying capacity in between, the halfway point of the plate being eaten of food and the entire plate being eaten, then we're slowing things down, concave down. Still increasing the amount of food in your body, but you're slowing the rate down at which you're eating it. All right, we're going to finish this up with another problem where you have to write the differential equation. And I got this wrong on purpose because I wanted to show you how delta math would do such a problem. Okay, so let's start by reading the problem. The rate of change dp dt of the number of foxes on an island is modeled by a logistic differential equation. So immediately, because I see that, I know that I'm going to use this formula because it says it was logistic. Okay, the maximum carrying capacity of the island is 534 foxes, so that means that the carrying capacity is 534. Immediately, I know what A is. The only problem is I can't find out what K is unless I do some work, right? So I have to solve for K. And in order to solve for K, what I'll need to do is use an initial condition. There's actually two initial conditions. The number of foxes on the island is 167. So that is a p-value at a certain time, right? At that certain time, the rate at which the foxes are increasing per week is 47, and that's going to be P prime. So when this p-value happens, this rate of change happens. Okay, that's important to know. And what the feedback in delta math shows you here is that in order to solve for k in this equation, right, you got to plug in your 167 for p and your 47 for your rate of change of p, and then you can solve this for k. And you can use a calculator to get this crazy fraction. I don't expect you to do this in your head or on paper at all, but just take 47 and divide by all this in your favorite calculator, probably Desmos, and you'll get the right value of k. And then you'll have to write down this equation, right? You'll have to write that down. There is an alternate form where they have 1 minus p over a, and there's a different k value for that, but I wouldn't mess with that. Okay. All right. So let me do another example of this all the way through. Now that we've kind of showed how that works out, and let me pick a different color here. How about there we go. There's a nice little Titan purple for South Garner. So we've got a logistic differential equation, right? So that means that dp dt is some constant times the population times a minus p, where a is the carrying capacity. The maximum capacity of the school is 772 students. So that's what this is. And then at 6 a.m., the number of students who heard the rumor is 217. So that's going to be at a certain time, we're going to have 217 students who know a rumor, whatever the rumor is. Taylor Swift is pregnant, maybe. Who knows? And then the rate of change when that number of people know the rumor is it's 46 students per hour, right? So the rumor is spreading at a rate of 46 students per hour. We've got to figure out what k is. So k is going to be 46 divided by all this stuff, which we can let Desmos crank out the crazy fraction for that, right? Let's use the College Board version of this. So 46 over 217 times 772 minus 217. And we're going to copy this fraction. 46 over 120, 435. Wow. Hopefully I did that right. 772. Just making sure that I got all the numbers right in here. 772, 217, yeah. All right. So that means that my k value that I just found is 46 over 120,000 something, 435. And then we're going to have p times our carrying capacity minus p. So that's the differential equation that should be used to model this situation. And it's really important to know that you don't have to solve this for p. Thank God. It's kind of a mess, but this is the differential equation. Okay. So again, we've got our carrying capacity. We've got some initial conditions where we know how many people know a rumor at a certain time and how fast the rumor is spreading at that particular time. The fact that it's 6 a.m. is totally irrelevant. We don't have to plug a 6 in anywhere because our differential equation does not depend on t. The population depends on t, right? The later in the day, the more people know about it. But this is just modeling how fast it's growing over time. Okay? All right, so that's all we've got. That's the idea, again, of logistic growth is that I can only handle so much on my plate, so there's a carrying capacity that you have to be worried about or concerned about, not worried, but concerned about. And remember that when half of the carrying capacity is reached, that's when the maximum growth happens, the inflection point of the curve. All right, until next time.